Okay, so this is a recording for Lab 3, which is another MATLAB code related to linear regression model and also system identification or sensor model identification, or to find a transfer function to discuss the behavior of a sensor. So what you need to do for this lab, you need to go to Canvas, then you go to Lab 3 under Files, then you go to Part 1, then you're going to download device A, which is here. This is device A. This is another encrypted code which represent a voltmeter in this case. So this voltmeter can measure any voltages from 90 volt to 150 volt. So there is an example code here which you can see what's the behavior of this voltmeter from 90 to 150 volt. So this is the example code. You need to type it by yourself, and then you need to, this example code is going to take inputs which are numbers from 90 to 150 volt, and it's going to apply it to this device, which is a voltmeter, and it's going to give you the measurement output. And this is going to happen in a for loop. And then you're going to see the actual input, which are the voltages that you wanted to read, and what has been measured with this voltmeter. So that is going to be, I mean, the best scenario is whatever the input is, the output be exactly the same. So that means the best scenario is for your voltmeter to have a regression model of just y equal to x. So that's a way that we can calculate the regression model. So there are the codes here to calculate the regression model. You can calculate B and M. So in your report, make sure on the theory side to make sure to write the formula for B and M. But in this case, you don't need to calculate it by hand. In this case, MATLAB is going to calculate it for you. But in the theory section or part of your report, make sure to write it down how to calculate it by hand. So what you're going to do, you're going to just run this code. I'm going to run it right now to explain how it works. So this is the code, and I download it. Make sure to download the device A in the same folder which you have and your workspace for your MATLAB is running. Make sure to remove device A's or sensor A, sensor B, and sensor C from previous lab. Otherwise, it's going to be confused and it doesn't know which one is the one for this lab. So I'm going to just run this. And as you can see, it's going to show you what is the measurement. So these are the true values on x-axis from 90 to 150 volt. Those are input values that you wanted to measure. And what has been measured with this voltmeter are in the blue dots here. So you can see here, it's almost great. It's almost perfect as far as measuring the voltage from 90 to 110 and from 120 to 150, but it's not really great from 110 to 120. So it's not giving you a great model, or basically it's not measuring very well. This voltmeter is not great for that. So obviously when you came up with a range of 90 to 150, the MATLAB code is going to give you a regression model, which is the black line. But this black line is not a good representation for this voltmeter, because if you use this model in order to predict what's the behavior of this voltmeter, you're going to see that it's the predicted values or measured values are here, but the actual measured values are here. So that's why this is not a good measurement model. So what you need to do, I would suggest you to come up with changing this from 90 to 110, from 110 to 120 and 120 to 150, and then find three different regression models. And then for different ranges, you're going to model the whole voltmeter for different ranges. So that is the first part of your lab, which the first part is just saying that uh, is there any way to find a model which is, I mean, your observation, I already talked about some of the observation that you're going to have. If you have any more observation, write it down. So then it says that, is there any way to model a linear model for this from 90 to 150? So you need to answer this. And then it's saying that, is there any way to find different models, one or two or three models, to describe the behavior of this voltmeter over the voltage ranges which we want. So the second part of the lab, what you need to do again, you need to find a sensor A. So you go to your canvas and then you go to your lab 3 part 2, and you're going to find your sensor B or sensor A. So this is sensor A. This is another P code, which is the encrypted sensor code. So there is an example code. So what you are going to do, you're going to find out what is the step response of this sensor. So imagine that this sensor is going to measure, let's say, 0 to 1 Pascal of pressure, and at a specific time it's going to measure it. So this sensor is not going to measure it really fast, so it has some delay to measure the value. So what is the important information you're going to get out of this is the fact that how many seconds or how many milliseconds you need to wait until you can have a good measurement signal. So this is a code which, not this one, I guess. Yeah, so this is a code. I changed a lot of things in this code. So for instance, let me see if I can have the same code as here. So in that case, so I'm going to run this code. So you're going to give input of this sensor 0 Pascal and 1 Pascal, or it can be anything else. It can be 0 volt and 1 volt at specific time. And then the sampling rate is zero point 0.1 second. You're giving this input to sensor, and then you're going to plot the output of this sensor over time. And interesting enough, you can see that interesting enough, you can see that this method is basically is designed for, there is sensor A is not existed. Oh, okay. I need to change this. Let me go to this first, change the folder. So I put it here. Okay. So if I run this now, uh, so if I run this now, you'll see that it's going to get sensor A. I need to close the previous figure. So you see, I'm just giving the same measurements, but it cannot measure the correct value, which is, let's say, it's supposed to measure 1 volt or 1 Pascal in this case, but it's not going to measure 1. It's going to measure 0.7 or 0.6666. If I click here, it's going to measure 0.6666464 instead of measuring 1. So that is not a good sensor, but the information which is the most important information for us is not only the final value they can measure, it's also how much of time, this is the time, the x-axis is time, so how much of time does it take to measure this value or to measure this 1 Pascal or 1 volt or whatever it is. So you need to modify this code in order to make it better. For instance, you can see here, this is the time that is wasted because of input. So you don't want to have this wasted time. So you're going to get rid of, for instance, these ones. So in that case, your ones is going to start from 0. So you are going to see exactly how much time does it need to get to the steady state value. So it's going to be more accurate in this case. Adding more 1, for instance, is going to also give you better results because you're measuring more and then you're going to get to the final value um, in with more samples. So you can also do some other things. You can use, for instance, some other codes like ones of these. You can have ones of 101. So in this case, you can give 100 ones to this sensor, which is going to be much more accurate in this case. So what you need to do, you need to answer the following questions. One of them is modify the above code to be more accurate, which I already explained some of that, how to do that. Conduct at least 1,000, and also you need to find the transfer function. So how you're going to find the transfer function, when you have this figure, I'm not going to give, let's say 100, I'm going to give in this case 20 of them. When you have this figure, what you're going to find out, you're going to find what is the final value. So the final value still didn't get to the final value. I may need more than 20 of them. I need maybe 50 of them to get to the final value. So I got to the final value. This is the final value. If you click here, you can see the final value is 0.6666. So that's the final value. And then you need to find what is the time to reach to 63% of final value. So you are going to calculate the 63% of final value. Then you are going to find what's the time to reach that. This is just example. This is not the answer that you're going to have. But one problem you're going to notice, because you want to get to 63% of final value, you're going to move this up and down, but you see there is a jump here because you don't have enough samples. One thing that you can do to solve that, you right click here, select style, and then mouse positions. And then when you move it, it's going to be more accurate. Move it until you're going to get to 63% of this value. And then that X value is going to be your time constant, or tau. And obviously for your transfer function, which is A divided by S plus B, your B is going to be 1 divided by tau, which is a time constant. So time constant is the time that it reaches, the final value reaches to 63%. And then how you're going to find A divided by B, A divided by B is this final value, which is the output measured value, which is 0.6666, divided by, let's say 1, and 1 is a true value. So that is B divided by A. So if you already calculate B using 1 divided by tau, so you can easily calculate A, and that is the transfer function of your system. So now the next thing you're going to do, you're going to also do the averaging. In order to average, you're going to repeat this input, giving the same input over and over for 1,000 times. So there are several ways to do that. I'm just going to show you one way. Let's say output average. So I initialize it with 0, and then I say for I equal to 1,000. Then I'm going to sum all of them. Let's say output sum, also output sum equal to 0. Then I'm going to have output sum equal to output sum plus whatever I'm measuring at each time step. And then at the end, the average one is going to be what? It's going to be this equal to output sum divided by 1000. So in that case, you're going to have output sum, then you're going to put output sum here, then you're going to repeat calculating the transfer function, and you're going to see if the transfer function you're calculating in this case is exactly the same as the previous transfer function, then there is no noise for this sensor. This sensor is not noisy. If it's different, then there are some noise. So what kind of information is given to you is just like a speed of the sensor, the steady state or the mean value of the sensor. These are the information with averaging that you can get. So again, if you have any questions, you can contact me and we can go through them.